SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 4, and we are going to discuss today the transformation of stress matrix. So, let me clarify, we are talking about the transformation of stress matrix, not the stress tensor. So, stress matrix, we have already discussed this. So, this is the representation, and by representation I mean the matrix form. Representation of the stress tensor in a coordinate system. So, this changes from one coordinate system to other. But the stress tensor itself remains the same, but the stress tensor itself remains unchanged. All right. So, you can recall the stress, if you want to get stress matrix of a stress tensor, then you first choose the coordinate system. It has 3 bases, let us say E1, E2, E3, and then you find out the tractions on the 3 planes whose normals are E1, E2, E3, and form columns from those tractions, and that is how you get your stress matrix, right. So, if you have different coordinate system which has different bases, then you have to find tractions on the different bases and then form columns from the tractions of the new bases. Okay. That is why the matrix changes from one coordinate system to the other, but the stress tensor itself is the same. So, can we somehow find out what is the relationship between the stress matrix in one coordinate system and the stress matrix in the other coordinate system? So, that is what we mean when we say transformation of the stress matrix. Okay. So, let us recall the stress matrix. So, sigma stress tensor for matrix I am going to put the big bracket. So, big bracket means I am looking at the matrix form, and then I also write down which coordinate system. Let us suppose it is E1, E2 and E3. So, this is then equal to the 3 by 3 matrix which has 3 columns The first column is formed by the traction on E1 plane, and that is T1. The second column is formed by traction on second plane, that is T2, and this last one is T3. So, the first column is basically the representation of the traction 1 in E1, E2, E3 coordinate system. Okay. So, you find out the components of the tractions and put those numbers in the columns. All right. So, if that is the case, I guess can we say that sigma I j, what is sigma I j then? So, j denotes column here, right. Sigma matrix has two subindex I and j, I denotes row, j denotes column, and we know from this matrix that the columns correspond to tractions. So, j means we have to look at the traction on jth plane, and then what does I mean? So, I means we go to the corresponding row or the corresponding component of that particular traction. So, sigma I j is basically traction T j dot E I, because I want to look at the ith component. So, I dot this vector with E I. So, that is how we get sigma I j, all right. And suppose now I want to write down the stress matrix in a new coordinate system, which let us say is E1 hat, E2 hat and E3 hat. Okay. So, I have that matrix again, sigma tensor is the same, we have the same stress tensor, but I want to find its matrix form in the new coordinate system, E1 hat, E2 hat and E3 hat. Okay. So, that is again by definition we know it is a 3 by 3 matrix, which has 3 columns, and each of these columns are the tractions on planes whose normals are the basis. So, this becomes for example, T1 hat, the traction on E1 hat plane. This is T2 hat, this is T3 hat, all right. So, you know this is the matrix form in the hat coordinate system. So, I will say that the components of the matrix is basically sigma hat I j, instead of sigma I j let us say it is sigma hat I j, all right. So, again if you look at the above definition, then you can very easily say that sigma hat I j is basically T j hat, is not it, traction on the plane whose normal is E j hat, and then you dot with. So, I have to now represent this traction in the hat coordinate system, remember not in the E1 E2 coordinate system, but in the E1 hat, E2 hat, E3 hat coordinate system. So, I must dot it with E I hat, not with E I. So, you have to remember, I will make it more clear that this is not equal to T j hat dot E I. This is supposed to be T j hat dot E I hat, because I need to find the components in the new coordinate system, because I am representing everything in hat coordinate system. All right. So, that is the definition of this stress matrix, but how to relate sigma I j and sigma I j hat. So, that is the question, how are these two related to each other. So, we are going to use the definition. Okay. I will write again sigma hat I j, that is equal to T j hat dot E I hat, and then let us try to write down T T j hat, the traction on E j hat plane in terms of the tractions on E 1, E 2, E 3 planes. Remember from the second lecture we found out the relationship for traction on an arbitrary plane in terms of 3 other planes. So, we are going to use that formula. So, let me switch back to the black pen. So, this is then equal to summation over some k equal to 1 to 3 T k times E j hat dot with E k, isn't it? Whether you write E j hat dot E k or E k dot E j hat, it is the same thing. Okay, so, you can look back at the formula, that is the formula for T j hat only, and then we further dot it with E I hat, all right, because this number here is only T j hat. Okay. So, this is also equal to summation I equal to 1 to 3 T k dot E I hat times E j hat dot E k, right. So, we had two vectors dotted. So, I clubbed them together. All right. Now, we have to somehow find out the relationship between E 1 hat, E 2 hat, E 3 hat and E 1, E 2, E 3. So, that means E I hat would be equal to some rotation tensor R into E I, all right. So, this R is a rotation tensor, all right. So, basically you have to relate one set of bases to the other set of bases, and you can always do it through this rotation tensor, all right. Now, you see this formula that we have here, this formula, this is coordinate free formula, because everything is tensor here. Coordinate free, I mean it is not relating to one coordinate system. So, it is a tensor equation, we say it is a tensor equation. You remember from the first lecture what are tensors, right. So, it is a tensor equation. So, let us try to write this in some coordinate system. Suppose I write this tensor equation in E 1, E 2, E 3 coordinate system. That simply means I have to write each of the vectors and tensors in E 1, E 2, E 3 coordinate system. Okay. So, I will say again, this is a tensor equation, it is a tensor equation let us write it in E 1, E 2, E 3 coordinate system. Okay. So, that is quite easy. What we have to do is I simply represent each of the terms there in this particular coordinate system. So, E I hat I represent in E1, E2, E3 coordinate system, that is equal to. So, that is going to be a column, okay, having 3 numbers which are the components of E I hat along E1, E2 and E3. Similarly, we have the representation of rotation tensor. So, since it is a second order tensor, it is going to be a matrix, and again I have to write this in E1, E2, E3 coordinate system, and then I multiply this with EI, and again I have to write EI in E1, E2, E3 coordinate system. But when you start writing EI in its own coordinate system, they look very simple. For example, when you express E1 in E1, E2, E3 coordinate system, that is simply 1 0 0, E2 is 0 1 0 and E3 is 0 0 1, all right. So, let us see if I is equal to 1, what happens to E1 when it gets rotated. So, E1 hat, that is equal to the rotation matrix multiplied with E1, which is 1 0 0. So, what is this? This is nothing but when you multiply, you just get the first column of the rotation matrix. So, what you get is R 1 1, R 2 1 and R 3 1. So, that is the first column. Similarly, when you see what happens to E2, so E2 hat is then the second column of rotation matrix and E3 hat is the third column of rotation matrix. All right. So, now, what can you say about R 1 1? What is R 1 1? So, R 1 1 is the first component of E1 hat, and in which direction we are taking the component? In the E1 direction, because we are representing everything in the E1, E2, E3 coordinate system. So, I will just write here that R 1 1 is basically E1 hat dot E1. Similarly, R 2 1 is basically E1 hat dot E2, the component along the second direction. So, what can we say then about Rij? So, Rij means it is the jth column. So, it must be the component of Ej hat, right, and it is ith row. So, it must be the ith component. So, that means this is Ej hat dot Ei, quite simple. So, we are going to use this formula that we just derived in the above equation right here. Okay. So, we are going to use that formula here. You see, we have here Ej hat dot Ek. So, what is Ej hat dot Ek? Any guess? So, that is Ej hat. So, that must be in the jth column of the rotation matrix, and then I find out the kth component. So, it is simply Rkj, right. So, this thing is basically Rkj. So, we have sigma hat Ij equal to summation over Tk dot Ei hat Tk dot Ei hat multiplied with Ej hat dot Ek, which is Rkj. So, let us write it there. this is R K J for k equal to 1 to 3. Okay, we can do some more things here. Let us now also try to write down T k in the E1, E2, E3 coordinate system. Okay. Just a little bit of maths and we will have the final result. So, we can say this is k equal to 1, 2, 3 and then T k is nothing but T k m E m, where summation is over m equal to 1, 2, 3, right. So, this thing within the bracket is basically the vector T k and then I expressed it in E1, E2, E3 coordinate system. So, we have T k m E m, all right. So, this thing within the bracket is T k, vector T k, and then this has to be dotted with E I hat, right, and then further multiplied with R K J. All right. So, now we see we have E m dot E I hat, and if we look at this formula, then what do you think, what is E m dot E I hat? That is simply R m I, right. So, we can now write this as double summation over k m T k m R m I into R k j. Okay. And then what is T k m? So, it is the mth component of traction T k. So, in terms of sigma I j, what is T k m? So, T k is going to be the kth column in the sigma matrix. So, it becomes sigma m k, right. So, this means finally that sigma hat I j is equal to double summation over k m sigma m k R m I R k j. All right. Now, we can do a little bit of rearrangement, we are almost there. So, this becomes double summation R I m. So, R transpose I m, see R m I is same as R transpose I m, remember from the first lecture. So, this times sigma m k into R k j. Okay. Now, you can see it is basically the product of the three matrices here. So, if you try to write this equation in the matrix form, then this is simply sigma matrix in the hat coordinate system, which is E1 hat, E2 hat and E3 hat, that is equal to the rotation matrix transpose times the sigma matrix times the rotation matrix. All right. So, that is the matrix formula. You see, the matrix in the hat coordinate system is equal to R transpose sigma into R, and all the three matrices here are in the E1, E2, E3 coordinate system. All right. So, that is how you can find out how the matrix form transforms from one coordinate system to the other coordinate system. Okay. Let me make a remark here. You see the way sigma is transforming, how was the basis transforming? The basis was transforming as E I hat is equal to r times E I. You know, you can find the equivalent way of how the components of vectors transform. Here we found out how the matrix transforms. You can also find out how the columns transform. If you have a vector V, you find out the column in E1, E2, E3 coordinate system, and then the column in E1 hat, E2 hat, E3 hat coordinate system. And if you want to relate the two, you will see that for a vector V, V1 hat, V2 hat and V3 hat, that is equal to this R transpose times V1, V2, V3. Okay, so, you see how the components of vectors transform. In case of tensors, we have two rotations, one gets pre multiplied R transpose and then we have a post multiplied rotation, because it is a second order tensor. With first order tensors, which are vectors, the components transform such that we only have a pre multiplication with R transpose. Okay. But what is to be noticed here is that you see the components of a vector, when you are transforming, it is with R transpose, is not it? You see here, whereas for the basis it is with R, not with R transpose. Why did that happen? It is because the final vector V has to remain the same. The vector V is the same, you are just trying to write it in two different coordinate systems. That means, in one case you have V I E I, whereas in the other case you have V I hat into E I hat. Okay. So, therefore, the basis E I hats transform with rotation R, whereas the components V I hats, they transform with R transpose. So, that R transpose into R, because you have product here, it gets cancelled and becomes identity. So, that the product is the same, product should not change, because you see both the summation has to give the same vector V, the vector has not changed, you are just representing it in two different coordinate systems. All right. So, I hope you got some point, the what is matrix and what is the tensor. So, they are two different things, right. Matrix changes, but the tensors do not change. Vector does not change, but its column, its representation changes. Okay. Let us work out an example of the stress transformation. So, an example, suppose that the sigma matrix in E1, E2, E3 coordinate system looks following. One by root 2, 1 by root 2, 0, 1 by root 2, 1 by root 2, 0, 0, 0, 1. Okay. So, that is a sigma matrix in E1, E2, E3 coordinate system, and I want to find out how does the sigma matrix look like in the hat coordinate system. And let me say how the hat coordinate system and the without hat, how are they related. So, suppose this is your E1, that is your E2 and this is your E3. So, E1, E2, E3, okay. Whereas the hat is the rotation of this basis by 45 degree around E3. So, that means E1 hat is going to be somewhere here, E1 hat, then this is E2 hat, and E3 hat is same as E3. Okay. So, this is same as E3 and the rotation is by 45 degree. So, you have to rotate about E3 axis by 45 degree to get the new triad. So, what can you say about the rotation matrix in that case? What will be the rotation matrix? So, this rotation matrix has to denote rotation about E3 axis by 45 degree. So, you must have learned from your first year mathematics class, this is cos 45 minus sin 45, okay, I am running out of space, 0, then sin 45, cos 45, 0, 0, 0, 1. Okay. So, that is the rotation matrix, which is also equal to 1 by root 2 minus 1 by root 2, 0, 1 by root 2, 1 by root 2, 0, 0, 0, 1. Okay. So, now you have to simply apply the formula, is not it? So, what will be sigma in the new coordinate system, which is E1 hat, E2 hat and E3 hat. So, that is going to be R transpose into sigma into R, and let us see what do we get from here. So, actually when you work out the product of the three matrices with R given here and sigma given here, you get a very simple matrix which is root 2 0 0 0 0 0 and 0 0 10. All right. What is the meaning of this matrix? It tells us, see, the second column is all 0. That means the traction on the E2 hat plane is 0. There is no traction on the E2 hat plane. So, if you look at two sections whose normals are along E2 hat and minus E2 hat, there is no traction between them. All right. What about the first one? So, that is the traction on the E1 hat plane, and that traction has got only the first component, which is along E1 hat. So, it has only got normal component. So, if you again look at two sections whose normals are along E1 hat and minus E2 hat, then the traction between them is such that it has only normal component. There is no shear component, it only has normal component. Can we somehow verify that this formula is really correct? Can we directly get that the traction on E2 hat plane will really be 0? So, yes, that is also possible. You can directly find out T2 hat using your formula. So, let me just show that to you. So, T2 hat, so as per the formula, that is nothing but summation over I equal to 1 to 3 of T I times E 2 hat dot E I, right. Now, this is again a vector equation. Let us try to write this down in the E 1, E 2, E 3 coordinate system. So, if you do that, so we have 3 summations here. So, first one for I equal to 1 we have T 1. Now, how does T 1 look like? So, you have to go to sigma matrix. The first column of sigma matrix is T 1, which is 1 by root 2, 1 by root 2, 0, right. So, this is 1 by root 2, 1 by root 2, 0, that is T 1 into E 2 hat dot E 1. And what is E 2 hat dot E 1? So, from R matrix what will be E 2 hat dot E 1? So, E 2 hat means I have to look at the second column of R matrix and the first entry. So, that is E 2 hat dot E 1, which is minus 1 by root 2. You can also look at it from this picture, E 2 hat dot E 1, the angle between them is 135 degrees, and you work it out, cos of 135 degree, that is minus 1 by root 2. So, here we get multiplied with minus 1 by root 2 plus T 2. What is T 2? That is also 1 by root 2, 1 by root 2, 0. From sigma matrix you can see that, multiplied with E 2 hat dot E 2. And what is E 2 hat dot E 2? That is R 2 2, which in this case is 1 by root 2. Okay. Plus T 3. What is T 3? That is 0 0 10 from your sigma matrix, multiplied with E 2 hat dot E 3. What is E 2 hat dot E 3? R 3 2, R 3 2 is 0. E 2 hat is basically perpendicular to E 3. So, R 3 2 is 0. Now, you sum these two, all the entries, what do you get finally? See, these two cancel each other. So, finally, you get 0 0 0, and that is what you have found out here also, right. The second column is all 0. So, that is a verification. Okay. So, after doing all this derivation, our final take home message is that the matrix transform in this particular way. Sigma in the hat coordinate system is R transpose sigma into R. Okay. So, that is about the transformation of stress matrices. So, with this I will end the lecture here. Thank you.